Hi, I'm Peter Kikalik, and this is my Module 3 presentation. For our scenario, we are examining plaques in the brains of two rodent models of Alzheimer's disease. One is a model which produces amyloid plaques, and another is a model which produces amyloid plaques along with tau pathology. We would like to examine pixel by pixel data of concentration of amyloid and zinc from 25 plaques to see to what degree they are co-localized within plaques. We also want to see if the relationship between amyloid and zinc differs between the models. Looking at our data, we see that our amyloid is normally distributed. Our zinc appears to be kind of normally distributed, but there's a patch off to the side that's a bit more concerning. We have a large sample size of 5,000, and we would expect to see a nice looking normal curve there, which we don't see. And we have equal size in our rodent model groups. We're interested in seeing if our relationship between amyloid and zinc varies per model, which involves testing of an interaction term. This requires us to center our predictors. This was straightforward for zinc. We just subtracted the mean out. For our categorical variable, we achieved this using contrast coding and specifically coded our variables so that the effect observed represents the difference of our dual transgenic mice compared to our amyloid transgene-only mice. Looking at our data, there appears to be a relationship between zinc and amyloid as they're increasing together, and it appears that the means of our two different rodent models differ, so we might expect to see a significant effect of our categorical variable. It looks like the slopes of the lines differ, which would indicate an interaction, but we need to take a look at our actual models. And looking at our nested model comparison, we see that our main effects are significant and that we also observe a significant interaction. Our model summary confirms these observations. However, when we go to our residuals, we see that while there aren't many outliers and it appears to fit a normal distribution, the residuals versus fitted plot has a bend in it. And the problem here becomes clear when we decide to visualize our data by plaque. The visualization shows that our data form discrete clusters based on which plaque our data is coming from. When we visualize these groups separately, we see that there is variance in both the slopes and the intercepts of our plots of amyloid by zinc. And we can use the linear mixed effects model to analyze this data. Variance in data like this can lead to inferential errors in OLS due to inaccurate parameter estimates and deflated standard errors. LME is designed to handle clustered data. And so we start out by calculating our ICC, which informs us that roughly 71% of our variance seems to be due to plaque-based grouping. So we know that's playing a significant role in our data. In selecting our model here, we want to select the model with the lowest BIC. Going from our OLS models to our mixed effects models, we see a large drop in BIC, with our main effects model showing the lowest BIC, 30,518. We can examine our data using the LME4 package by Douglas Bates. Using this package to conduct our analysis, we break up our model into fixed effects, which represent our population level effects, and random effects, which represent the variance present due to clustering in our data. Looking at this model, we see that we only observe a significant fixed effect of zinc, called level 1 in here. We also have a complex error term where we have our residual variance, about 25, but we also have the variance of the intercepts of our groups, around 28, and then we see about 0.22 variance in the slope of the relationship between amyloid and zinc. We observe a correlation in our fixed effects of our zinc effect and our intercept. We're not super interested in the intercept, so there's not too much to make of that. We also see that correlation in our slope of our intercept and our random effects equal to about 0.6. These are indicating that the shift in the intercept and slope seem to be related, but I'm not totally sure what this means in particular about our data. Looking at our diagnostics, we see no evidence of multicollinearity. We see that the bend in our residuals is gone. We still see normality of our residuals, and our Cook's distance values indicate that we don't have any outliers. And so we can sort of look at what went differently in our two models. In going from OLS to LME, we see that the significant effects of our categorical variables and interaction term have both disappeared, which seems to indicate that the variance that was being detected as effects in OLS are no longer present in our fixed effects, and instead we see these effects, these random effects of our intercept over in our complex error term. Our fixed effects for our intercept and level 1 zinc variable seem to be similar, though we know that our LME estimates are more accurate in data like this. And going off what David Friedman discussed, we now want to make sure we direct future experiments to test phenomenon we're interested in. We want to make sure we're not just trying to optimize the fit of our model, but that we're actually using well-designed experiments to test the hypotheses we're interested in. Expanding on that idea in the context of our data, from here we would want to better understand what is causing the clustering in our plaques. In this case, it looks like our plaque grouping is acting as a proxy variable, which appears to show variance in the intercepts of our plaques. We could try to look and see if the zinc content of the surrounding tissue is a factor, or perhaps try to include the brain region the plaques are located in and see if that helps explain the zinc content.